The title, I don't remember it now. The title of this intro of this lesson is Arithmetic Sequences and Series. Now, you guys already know what an arithmetic sequence is.
Yeah.
At some point, it has been put in front of you what an arithmetic sequence is. Does anybody have any idea, shot in the dark, anything?
2, 4,
No.
6, 8, 10.
Yes, that would be a very good example. Good job, Cole. What?
5, 10, 15.
Yes, that would be another example. But what? Okay, but what is happening in, let's take, we're adding what? We're adding 2. What about in Caleb's?
5.
We're adding 5. So with an arithmetic sequence, we are consistently adding by the same thing. Let's see. This, if you had algebra with me, which was literally impossible, this is the slide that you would have seen about an arithmetic sequence. Which, if you want to jot it down, you can. But it's a little bit of a review. An arithmetic sequence, or in an arithmetic sequence, the difference between consecutive terms is the same. So, like in Ryan's, it was 2, or Cole's, it was 2, Caleb's, it was 5. Yes, question, Ryan.
Can you multiply 2?
That would be a different type of sequence that we will get to on 8.3. We can't subtract. So, it says common difference. That would be either adding or subtracting. Yep. And that is what, so here's Caleb's example. He must have looked at the slides ahead of time or something. 5, 10, 15, 20, and so on. The common difference is 5. That is what you would have learned in algebra. Again, if you had me for algebra, this is what you would have seen on page 244 of the algebra textbook. Seem a little bit familiar-ish? Now, here's what we add to it with an algebra. If our series, or our sequence, I need to keep those terms separate, was 5, 10, 15, 20, and so on, we would consider those terms to be the range of our sequence, and the domain is just its position. So domain will be 1, 2, 3, 4, and so on. If we were to graph this, let's say 1, 5, it would look something like this. It would be a line, but we would not connect the points because we only want its position of 1 and its value of 5. Right? We only want this point. We don't want like 1.5, 7.5. We want 1, 5, 2, 10, 3, 15, and so on. What type of... Nah, I see what you're thinking, but we have 2 different types of... It is linear. Point graph is not exactly where I was going. Not exactly. It's either... so exponential would mean that it's curvy, but we have graphs that are either continuous or discrete. This would be discrete because we are not connecting these dots. It is only the point 1, 5, 2, 10, 3, 15, and so on. So when we are looking at these sequences, and if we ask you to graph them, they would be a discrete graph. If you were to draw a line through these on like a homework question, when you're asked to graph, that would be incorrect because I don't want these in-between points. Now, we call this an arithmetic sequence, right? And we get a pretty good idea of what that is. Here is the formal definition of that. A sequence is an ordered list of numbers, which we've got that idea, 2, 4, 6, 8, and contains a domain and range. Well, we just looked at that. Its position, if it's first, second, third, fourth, fifth, whatever, is our domain, and our range is the actual term. It's the actual value. Is that what it just says in the following? I typed that this morning. I should have remembered. The position of each number is domain, and the value is the range. Perfect. The values in the range are called the terms of the sequence. I did just talk about all that. Now, one side note, like what I say right here. Hey, stop being mean to Annie. Like I say right here, our domain could start at 0. So if they gave us our sequence and they put it in like a table form and it started at 0, that wouldn't be incorrect, but most of the time our domain starts at just 1, like it shows up here. Any questions on that? We knew this stuff already. We have seen this before. What we are adding to it is calling is naming a domain and naming a range. Those two terms are really the new stuff that we're adding here. Now here's a little bit more new stuff. There are two different types of sequences. A finite sequence and an infinite sequence. Did you in algebra? I don't think my algebra class touched on it, but we were virtual, so everything was kind of chopped down to the bones. When we look at a finite sequence, obviously finite, right? Limited number of terms. This notation is something that we probably are not used to. This would be considered like set notation right here. So in a finite sequence, we could list the entire domain, right? We could list all of the terms. We also could, I didn't write it here, we could list the entire range. And we use those nice curly brackets when we are, listing our domain or range in these sequences. So say n was 4. Our domain would be 1, 2, 3, 4. And let's say we are using Cole's example, 2, 4, 6, 8 would be our range. Have we seen notation like that before with those curly brackets? I don't think so. Set notation, yeah.
Why would that be finite? Just can't that go on forever?
Well, it could, yes. But if we only want this set right here, if we only want the values 2, 4, 6, and 8, then it would be finite. We can decide. Oh, right here, 2, 4, 6, 8.
You know the game sequence?
I do know the game sequence. Doesn't have a whole lot to do with this.
Well, kind of.
It's a finite set. Yeah, sure.
It has to be like diagonal.
Yeah, all that good stuff. Infinite sequence. On the other side, obviously a function that continues without stopping. Now its domain, so all the possible x values, right? Like its position is the set of positive integers. Now, this is not in our textbook, that symbol, but if you move on to higher level math, you will see there are different, we talk about integers. You guys have heard that term all the time. That's like counting numbers. You guys have heard of, what other sets have you guys heard of? Integers might be the only one. But the math symbol for integers is z, and if we're talking about positive integers, you put a little plus in the exponent. So you don't have to necessarily know that, but that's just for free. There's college level math for free in your high school class. You're welcome. Did you say thank you?
No, he said bingo.
Oh, well, it sounded like it. But anyway, just making kind of a side point there. The difference we would see in an infinite sequence is the 3 dots, right? If I wanted all even numbers, 2, 4, 6, 8, 10, 12, and I would put the little dots after I list the first few. So 2 different types of sequences. Why don't you go ahead and do numbers 1, 2, 3, and 4.
That's a finite sequence.
Shh, that's what you needed to. Well, all of them technically are infinite sequences because they have the dot, dot, dot. So they would keep going. But you need to decide if they're arithmetic. And when it says explain your reasoning, the explanation would be because there is a common difference, and you would give what that common difference is, like it's adding 2 every time, or because there's not a common difference. So you need to tell if that is arithmetic or not. Here's my clicker. There we go. Oh, I had an example I was going to show you. Would you guys like to see an example of number 1, 2, 3, or 4, or are we doing okay? Yeah. Uh-huh. So that would not be arithmetic. We will talk about it later. That would be geometric, which you guys have also looked at a little bit. Mm-hmm. But today we are only looking at arithmetic sequences. Go about 30 more seconds to finish those. Okay, let's keep going. Now this was the example I was going to show, but we'll use it for something else. Let's take these numbers that they give us in letter A. We can see each time we are adding 7. So this would be arithmetic. Our common difference, which when we talk about our common difference, that is the variable d, is just 7. Now, what if I said, I want you to give me the 156th term? Now, if you're Trey Ferfinsky, you probably are making a table that goes up to 156. Is that fair to say, Trey? Yeah, probably. Okay. If you are paying a little closer attention in class, then hopefully we'll be able to write an equation and we'll be able to just find the 156th term. This is the equation you've seen before. It is a rule for an arithmetic sequence. If we want to find, and we call that the nth term, if we want to find the 156th term, instead of writing a table up to 156, we can use this equation right here. And I will, after you get that jotted down, then I will go over an example. Yeah. What? That's the same slide that we had earlier. Did I duplicate slides? Freeze. That's okay. We can apply this example to these problems. Did you guys need a little higher up? You need any of this? Sorry. Go ahead. Go ahead and finish. About 10 more seconds to finish up. Okay. So if we were to, well, why don't we look at number 5, letter A. It says, we'll cancel this out here. It says the first term is -5. So we would write that as a sub 1, right? When we see the value of n, that's talking about what term is it? Is it the first, second, third, fourth, fifth? What term are we talking about? So when we write a sub 1, that would be the first term. The first term is -5, so a sub 1 is -5. And each term is 4 more than the previous. So if we're adding 4 each time, what would the common difference be then? It would just be 4. Now, we want to write an equation so that we can find a sub n. So I can say 156, and then you can plug in 156 and find that value. We would write our equation as a sub n equals a sub 1, which is -5, plus n minus 1, that's our term, n, multiplied by our common difference. Now what you will see a lot, and even in the answer key, is that this is not the form in which the answer is written. All right, we do a few things to simplify it. Now, I'll have to double check with Mrs. Shoup to see if this is something that we accept as like a simplified form or if we need it simplified all the way. For now, let's say we need to simplify. So that would mean that we are going to distribute the 4. And then we're kind of going to, we don't call it slope-intercept form because we are not writing a line. We have discrete points. But we are going to write it in slope-intercept form. Yes. That would be what we plug in. If I said find the 156th term, that would mean n equals 156. We plug it in. Again, this would be what we consider simplified form at this point, unless Mrs. Shoup tells me something different. What is this? Again, we're not writing a line. It's discrete points. But what would this negative 9 be? Our y-intercept. So, oops, negative 9. So what term would that be? We said our first term right here is negative 5. Not quite the last one. It would be our 0 term. Yep, like we said, our domain might not always have a 0 term, or they might not list 0 term. If we look at a list like this, we assume that this is our first term. But when we write it in this form, we do find what our 0 term is. Just as kind of a side note, big picture. Go ahead and do letter B. I'll leave that up there. If you finish letter B, then I'm going to do number 6 and then let you guys take like a minute to do 7, 8, and 9. So if you finish letter B, then you can try 7, 8, or 9. But I will do number 6. Take about 10 more seconds to finish letter B. All right, now if we look at number 6, here we go. Our first term, ignore this. Our first term is 15. Our common difference, they're consistently adding 7 in number 6. So if we follow our formula, we have a sub 1 plus n minus 1 times our common difference. Now we would just need to use a little bit of algebra to distribute and simplify. Now in 6, 7, 8, and 9, it says find a sub 20. So we just wrote a rule for the nth term. So there's part 1. Now to find a sub 20, we would write it like this. A sub 20. Part of this being a little bit difficult is getting used to the notation. So it might not all snap back today, but I think we will get used to this notation. A sub 20 equals 7 times 20 plus 8. That gives us 148. Yes?
Would it just be like easier to make a table?
Well, if you need to find like the 5th term, then maybe.
Oh,
But if you need to find like the 80th term, then,
why don't you just make it really long?
well, you could. You could. That might not, work out awesome though.
It's one way.
That is one way. Hey, if you're panicking on a test, then make a table.
I will.
There's lots of paper over there. Go ahead, work on 7, 8, 9. Now, if I ask you for the equation, then, at best you're going to have credit if you make a table. If I ask you, write the equation and then solve for something, you only did part of it. You only solved. This is true. Yes.
Instructions, so we can get like
3/4 credit.
Or I could write the equation and get full credit.
Yes, you could do that too. Lots of options.
Can it be a negative number?
Yes. Our common difference, as long as it's consistently adding or consistently subtracting.
No, I mean like how you got 148. Can it be negative?
Yes. Yep. Like for number 7, it will be negative.
Okay.
Do you have to graph in those two? No, that's on the backside. Take about another minute to work on 7, 8, 9, and then flip to the backside. I'll show an example of what you're looking at on the backside. Yeah. You have a question, Aiden?
Yeah.
Which one? Number 7?
Let's put it after the negative right now. How would we find that?
So for number 7, our a sub 1 is 62, right? That's our first term. Plus n minus 1. Then, like you said, the common difference is negative 9. So now we need to distribute this negative 9. Oops. Well, we're going to introduce something new in a second. Sorry.
Yeah.
But we're not going to practice it till tomorrow. Mrs. Shoup's class is doing 8.2 and 8.1 today. Worksheets for it. We're learning pretty much everything we need to for 8.2 and 8.1, but I did not have time to look at the 8.1 worksheet, so we are not doing that today. Yes, let's go.
Let's go. Let's go.
That's number
boys.
7.
Let's
All right,
Wait,
whoops.
it's like 30 more seconds.
Graph, you don't need a graph 6 through 9. Okay.
I believe I was joking.
Oh, funny, Trey. Or, I don't know. Now, this is where things get a little bit tricky. We've never seen a problem like this before. One term of an arithmetic sequence is a sub 19, so the 19th term is negative 45. The common difference is negative 3. We need to write a rule for the nth term. So just like we were, except this time they start out by giving us a little different information. Then graph the first 6 terms of the sequence, which I'm not going to do right now. I'm going to let you guys do that on your worksheet, but I won't take the time to do that part. If we need to find, well, what do you guys think? How do we even begin to try to solve this? We know what the 19th term is, and we know what the common difference is. How are we even going to begin to write an equation? Yeah, Ryan? You could plus 3 all the way back until the first term, so a really long table. Yeah, we can. So that's a start. Very good, Caleb. We don't know what a sub 1 is. We're still trying to find that, right? What else can we fill in from our equation? A sub n. What is that? What do we have? We're looking, or they give us the 19th term, so we put 19 as. They gave us the value of all of this, negative 45. And we have the common difference. So we can solve for our first term. Very good. Wow. Proud teacher moment. 18 times negative 3. This is not a number. This is just for your learning. Then you'll get to show off your learning with number 11 and 12, which are very similar. Let's see. 18 times 3.
64.
No. 54. Now it said that we need to write an equation, right? So we found a sub 1, which we need to write our equation, but we haven't written our equation yet. A sub n equals 9 plus n minus 1 times negative 3. Now we need to write our equation in a nice form. So a sub n equals 9 plus, minus 3n plus 4, not 4, wow. I have been off my game today. So that would be our final answer. If I added right, which I did. Yes, I did. Now, like it says, it wants you to graph the first 6 terms. So you would need to plug in, this is where you would make a table. Three, 4. You need to plug in your first 6 terms, see what they are, and then plot them on a graph. Should your graph have a line on it? Like, should you draw a line on it?
Yes.
No, but should it create a line?
It could.
Think about that. It should, yes. But you would not draw a line. Now, instead of plugging 1 in for n, and then 2 in for n, and then 3 in for n, what's a really quick way to get those values? No. We could take our calculator. We could put this into our y equals. And then 1 will give us the first term. 2 will go to the table. 3, see?
It was that easy. I'll just do like 3 times.
Go ahead, do number 11 and number 12.
Alright.
Yes,
Say
I
so.
can.
I mean, I guess. I don't
11 and 12.
Let's go.
You also do need to graph those. No, it is not. It is not written yet. I started it. Like I said, totally ran out of time. So I didn't even get to finish this key. On which one?
How do you know you did something wrong?
Oh, did you distribute 4? Yeah. 4 times. Well, here, 4 times 9. Oh, 4 times 8, sorry. Yep, 4 times 8, my fault. 32. This one is 3. That looks good. Yeah. That looks good. What part of it? So let's see.
The first time.
It's 3, and that's correct. That works.
Oh, I was adding the wrong No, that might do it.
Yeah.
3 instead of 4.
Which, when you write it in, like, I hate calling it y-intercept form, but that's what it looks like, then it's you don't see your common difference. Well, you do, but it's not on the end like it was. It would be your slope.
Wait, so we're writing, we're graphing?
You are graphing. I think the directions say right in them, graph the first 6 terms. Yes, one of them has that, and I don't know how to get it off. There's the drinking fountain calculator. Yeah, I don't know how to change that.
How does the holy calculate?
Is it legendary number 42?
I mean, you can.
I don't know how to change it. Oh, I could probably just reset it, but also I feel bad. Someone. Oh. Are there any good ones? Oh.
Yeah, I keep those the same.
That's what I was doing, like the whole SAT. I got into there and I just started playing it.
There's a playground.
Playground?
Interesting.
Where do you go?
Is it one of those good wooden playgrounds?
Yeah. Ooh, drink it down. That's a nice person.
It's a nice experience right there.
Ooh.
Did you write that? Those steps.
How are you guys doing?
They really give you all the information.
Well, I'm there. Well, I'm sorry. Table. Sure, you know what you're supposed to be doing.
No.
How you doing there?
Honestly, let's just make a graph, dude. You have to change the end to that
Oh.
about another minute.
Is there a way to like?
Am I supposed to graph this? It's like way.
Yeah.
It's like, wait, what? Huge numbers? You can just.
No, it's just to put the plates on, like how it.
Yeah, if it looks. How do I not have any more?
Ryan, what did you have to
Is there a way?
What is the first point?
That's not what I got.
So if it's here, I mean,
Yeah.
maybe you don't need it to take up your whole page, but even if your scale, like on your intercept, on your y-intercept, maybe this is 50, 100, 150, or even something like that. Yeah, maybe your scale's 50s.
Is there a way to like? It's like my x values are at like 2,000. Is there a way to get to 1 really quick?
Yeah, a couple people had that same issue. So if your table is way off, that's one way with your. I think that just affects your graph, though. I don't think that changes your table. You can hit second. Wait, is that Cole's calculator? Let Cole. I'll walk him through it. Hit second window right up top, which will give you table set. And then it says table start. You can hit 0, and then the change in the table, which is the next line. You probably just want it to be 1, and then go back to your table.
That's a lot better.
I was gonna say you're gonna go over now to the next video. Yeah.
Yes.
6 terms. What a shot, man. Hey, Ryan, are you golfing?
Yup.
Where you going golfing?
Never mind.
Where?
Weekend?
Ryan, do you guys have something going on?
Can I be your caddy?
Where'd you go?
Can I show you bags? I could be your caddy.
All right. Let's look here. Oh, virtual student.
40-minute lesson.
No, this is. We're just having a conversation about a few things. You guys are getting your homework done. It's no big deal. Virtual students will have to do a lot of fast forwarding.
Well, how are they supposed to
Last-
know when to stop?
In this class, 3.
Who's those 3?
I don't know if that's protected information or not. So
No, you can say. You can say.
I don't know.
We'll keep the
I don't think
score.
it's not medical. It's not medical information.
Yeah, so you can't say. I would be offended if someone said
Levi.
All right. Let's look at the last type of question.
that. They don't have a mask on.
So, well,
Oh my god,
focus. Let's go. Let's go.
You better
Come on. We got 10 minutes. There's no reason for you to have homework. We should get this worksheet done. I have one more thing I need to go over too. So you're only going to get like 2 minutes to do one of these. Look, in this situation, they give us the 7th term, and they give us what it equals. They also give us the 26th term and what it equals. Now, let's fill in the information. We know that a sub 7, whoops. We need this in the back of our mind. A sub n equals a sub 1 plus n minus 1 times d. Now, we have a sub 7 is 17. So we know 17 equals a sub 1 plus, what's our n value? What's our n value? There we go. And we don't know what our common difference is. Well, tell me what you said one more time. I didn't quite hear you.
uh,
19? Yes, that would be a way to find the common difference. I'm going to show something else, though, so we can find our first term. That is correct, because you know it's going up by the same amount every time. So if you do 93 minus 17 divided by 19, yep. So we wrote everything we could to write an equation based on this information. Now, let's write everything we can to write an equation based on this information. Still don't know our common difference. This is true. Now, we know that these two, we'll call them equations that we wrote, are really representing the same idea, right? It's representing the same sequence. So one strategy that we can use is to solve this system by subtracting these two. So we have 17. Whoops, I put them upside down. Dang it. Well, let's see if it makes a difference. I think we might be off a negative. 17 minus 93 would give us negative 76. A sub 1 minus a sub 1 would just zero out. Now we have we have 6. 7 minus 1 is just 6. 6 minus 26 minus 1 is 25. No. What is that? Negative 19? Times d? We could just divide. It would equal 4. That follows the same process of what Annie said to do. Yes, that does not use our terminology whatsoever. But it does. I will summarize what Ryan said and what Annie said. We know what a sub 26 is. We know it's 93. We know a sub 7, or the seventh term, is 17. If we know with an arithmetic sequence that it's consistently going up by the same thing, we can do 93 minus 17, which would give us 76, and we can divide it by how many terms are in between those two, or how many positions are in between those two terms, which would be 19. And that would give us a common difference of 4. Now, no matter how we find the common difference, what do we need to do to find a sub 1? We do need to plug 4 in. So I'm going to erase here. We know 17 equals a sub 1 plus 7 minus 1 times 4. And a sub 1 would equal negative 7 degrees. Or 7 degrees. Negative 7. I know that was messy. This setup will work to find our common difference, solving systems. But I'm assuming, and I know I erased it, but everyone liked what I probably did second a little bit more. I think that makes a little bit more, I don't know if common sense is the right word, but it's a little more natural. Why don't you take 1 minute to do number 13, and then I just need to show something, and we will practice it tomorrow. But I need you to stay with me for a couple minutes after you do number 13. Shh. Levi, shh. Bless you. All right, 10 more seconds.
Bless you. Easy, man. Free.
I think you're allergic to Caleb. The COVID sneeze. Yep, that's
I'll get you.
a popular one. All right.
I'll get you.
Good segue.
Yes, you guys can put, you don't need to write, well, you might need to write down a couple of notes. We will review this again tomorrow. I just want to quickly go over one thing while we are doing well and in a pretty good mindset. Now, this lesson was sequences, arithmetic sequences, and arithmetic series. I just want to talk about for a second what an arithmetic series is. It is not on that worksheet, so we will practice it tomorrow a little bit and look at it more tomorrow. We know that a sequence is just the listing of terms, right? Now, a series is when we add an entire sequence together. So like it says, when the terms of a sequence are added together, the resulting expression is a series. Series can be finite or infinite. A finite series, we can figure out 2, 4, 6, if our series, let me backtrack. If our sequence was 2, 4, 6, 8, we can find what that series would be by adding each of those together. That would be a finite series. We can just find it. 10, 18, it'd be 20. That would be the value of that series. Also, we will look at infinite series and how we can try to sum up infinite series. So 2 different types of series, just like there's 2 different types of sequences. The notation that we use when we talk about a series is called summation notation. Now, have you guys seen this symbol before?
Yeah, backwards.
Sideways and.
It's the sigma, which is a Greek letter, but no, it's not E, it's sigma. It is, hang with me, like 1 more minute. I've got this slide and 1 or 2 more. This slide and 2 more. Come on, 2 more minutes. Give me 2 more minutes. When we want to talk about the sum of, let's say, this sequence right here, or these numbers, this is the notation we would use to write it. I represents the position, just like it would be the same idea as what n was. Keelan. Only if we're done with everything. We're not done with everything. I said 1 more. You guys keep interrupting me and being distracting. I'd be done by now.
Guys, pay attention to the back.
You're like the worst of it. I would be our position. That's the same type of idea as n, but when it comes to a series, we just call it I. We have 4 terms. Literally, I have not made anyone work till the bell yet this trimester, so I think we can hang with me here. We have 4 terms, so we are taking the sum from our first to our 4th term, and this is kind of what's happening. We'll talk about that more tomorrow. This is what we would see with an infinite series. So there's a really quick explanation of our notation. Now, if we wanted to find and add a whole series together, we could do a whole lot of work, right? We could find each term of a sequence, and then we could add them all together, which is a valid thing if we panic on a test. Instead, we do have a nice equation with some things that are familiar with us. We have n, right, our number of terms, a sub 1, which we've seen before. A sub n would represent our last term, so things that we've seen before when we are adding together these sequences. And that's all. Go ahead, pack up.
Oh.